dr, because we want to find dr. Dr of this using the what we call the chain rule. Okay, so dr du1 du1 plus dr du2 du2 plus dr du3 du3. Okay, and what is dr du1? If you remember, dr du1, which is the tangent vector, and then you differentiate with the dr du, we differentiate with its absolute, we have unit tangent vector. But this is also, if you differentiate, you differentiate with u1, you will get the tangent vector, which is the basis vector, e1. This is basis vector, e1. And what is this? The modulus or the absolute, the magnitude of dr du1, we call it scale factor. This is scale factor, h1. So h1, h2, h3, all are scale factors. Okay, those the h1. So now we can say that dr du1 is to h1e1. Okay. Now kita masuk sini. So we plug in here. So h1e1 du1, or we can rearrange it. Better put h1 du1 first and then e1 later. Because it is a basis vector, so you can rearrange. So h1 du1, e1 the basis vector, and this the same thing, the h2 du2, e2. Okay, this is h3 du3, e3. Okay, very easy. So now we look at the difference in position vector for spherical coordinate, dr, er, r d theta, e phi. So what is h1? So you can find h1, h2, h3. What is h1? Let's see. What is h1? You can compare this. Okay, try to compare this, and then this is dr, and this is the same as dr er plus r d theta e theta, okay, and then r sin theta d phi e phi. Okay. Kalau tengok sini, you dah nampak jelas. So we h1, h2, h3 we senaraikan, u1, u2, u3, and even you senaraikan dia punya basis vector e1, e2, e3. So h1 is equal to what? Okay. Okay. Now kalau tengok h1 is what? 1. Okay. Why? Because the dr is du1. Okay. dr is du1. So r is u1 is r. So depan dia tak ada, dia just 1. Kan? h1 is 1. So h2 is what? R. Okay. h3 is r sin theta. Good. Okay, u2 is very easy. u2 is theta. Okay. u3 is the phi. Okay, u3 is phi, and then e1 is er. Okay, e theta, e phi. Okay, very easy. Got it? Okay, now we just plug in there. Plug in. Okay, what we want to plug into? We want to find the Laplacian of this. Laplacian lot being used. This one. three-dimensional Schrodinger equation. Okay, it is at the very basis of the quantum mechanics. Okay, this one is so you want to find this Laplacian. So Laplacian, you write Laplacian very easy. First you H1, H2, H3, and then open up, and then du1, and then okay, you have this one operate upon all this thing, which is if you put du1 here, that means H2, H3 is always like this, and then H1 here, and then du1, and then the operator is here. If I put some sample A, so what you want to operate is here, okay? But we just want to find the operator. I mean the template. This is the template of the Laplacian, and then you want to find the operator of the Laplacian in spherical coordinate. Okay, du2 h2. Okay, 1, 3, and then h2, and then du2 plus du3, and then h. Okay, h1, h2, h3, du3, and then operate, and then you close the bracket. So just plug in the thing. Okay. Okay. H1. Okay. Mana kita dapat tadi? This one. Okay. H1, H2, H3. We have R squared sin theta. So H1 multiplied with H2, H3. You plug in. So we have R squared sin theta. Okay, we have this one du1, which is dr, and then differentiate. This one is what H2, H3, H2, H3, R squared sin theta. Just plug in, and then divide by H1, which is 1. No need to divide by H1, and then dr. Okay, and ready to operate. And then plus u2, the theta, and then H1, H3 is 1 multiplied H3 R sin theta, and then divide by H2 R. Okay, so you divide by R, so that means you just only sin theta here. So R or divide sin theta here. So and then du3 is du3 d phi, and then this is H1. Okay, H1, H2 is R, right? du3, so H1, H2 is R over R sin theta. That means 1 over sin theta. So R over R sin theta with R 1 over sin theta d phi. That's it. You got it. This is the ready to operate. You can just multiply, can simplify this. Let's say, for example, this one you can take out sin theta. So, for example, you can take out, if you multiply, or you open the bracket. So this one is 1 over R squared sin theta. Okay, 1 over R squared. Apa kita just buat slow. 1 over R squared sin theta dr R squared sin theta dr. Okay, and then this one also 1 over R squared sin theta, and then this is d theta, and then sin theta d theta. Okay, and then you have this one is 1 over R squared sin theta, and then d phi, then 1 over sin theta, and then d phi. Okay, you open up already. This one you can just r, because this one is you differentiate with respect to r, but there is sine theta out here, so you can just take this out and divide by this, because it's not dependent on r. Okay, so but r square you cannot take out, because r you have to differentiate with respect to r here. So you just can take out sine theta. So because sine theta is r, so we can cancel with this. So what left is what is r squared d r. Okay, and then this r also squared, and then d r is simplified just like that. And then the other one is, okay, all related, so leave it like that. 1 over r sine theta. See, you cannot take out sine theta because this is differentiate with theta. So just left, just leave like that. So d theta is the same thing, sine theta d theta. And then this one is very easy. You can take out sine theta. Okay, you can take out sine theta and multiply with this. So you have okay. 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 No need dah. Sorry. 1 over r. Okay. 1 over r squared sine theta, you just leave it like that, and then d theta, and then this sine theta d theta, and then this one very easy. Take out 1 over r squared sine squared theta, d double, you just double differentiate this with phi d. Okay. So you get the okay, no need to. Okay. Just like that. This is the final one. This is the simplified one. So you can leave it to here. You over here put until here put it is still okay, because you can just operate until here still okay. You can just operate, concentrate operating here, and solve. Okay? And this is the final one. Okay, that's how the Laplacian is derived. Laplacian in spherical coordinate is derived. Maybe you pernah guna last time. You pernah guna last time. Have you learned this? Very good. So today you learn. Maybe last time you just learned Cartesian coordinate, right? Cartesian coordinate very easy. I don't talk very easy. Very easy. So this is a level a little bit higher and being used a lot in physics. This is spherical coordinate Laplacian. Okay, let's say for example this one very easy. Okay, you can get the what we call the curl. Curl is being used a lot also in physics, in electromagnetic especially. We use a lot in electromagnetism. in apa what we call in Maxwell theory, Maxwell field equation. The first day I taught you about Maxwell field equation. Okay, so let's say for example you want to curl magnetic field B. What happened? Okay. So you curl magnetic field B in spherical coordinate, given B in spherical coordinate. Okay, B in spherical coordinate. B, they have the BR, ER, B theta, E theta. You can try also at home. You can try also doing the same thing with cylindrical coordinate, which is more easier. Cylindrical coordinate. B phi E phi. So this, let's say this magnetic field given like this. So obviously you want to find this, the what we call the spherical coordinate of curl. Curl is spherical coordinate term. Okay, very easy. You just plug in. So H1 E1. You just put ER. H1 is 1. H2 E that means r e theta. That's it. And then this r sine theta, which is the history e phi. Okay. Okay, and then the other one is the differential. Okay, the u1 is r, this one is theta, and then is d phi, and the other one is okay combination within this. Just plug in what we call br. Okay, br, okay, 1, there's nothing 1, so br only. So now r b theta, okay, r b theta, and then is r sine theta b phi. This is not a head. This is vector. No need to put. But this is a scalar already. This is a component, vector component, not a vector at all. So b r b theta, r sin theta b phi. Okay, this is a component b theta, b r b theta a phi. Like if you in my notes, okay, this a instead of a, b, now b. Okay, magnetic field. So we just took this b1 become br, ba2 which is b2 become b theta b phi. Okay, now how you going to do this? Very easy. Just simple calculation of determinant, of determinant of this. So cross product. So you take one. You take this one is this one. This one operate upon this. This theta operate upon this. This r sine theta. That means you can take out theta later. But I just plug in. You just can do later at home. R sine theta. That means you can take out r. Okay. And then this one b phi. R sine theta b phi. You operate upon this. B phi. And minus this one. This one operate upon this. Okay. D phi r b theta. Okay. And then this is e r. This one. And then plus. If you plus, you have to switch a little bit. Okay. Just now from left to right. Okay, left to right. This one operates. Now you have to here to here. You have to switch it because actually if you do from right to left, it will be negative. So you want to maintain the positivity. So just take this one, operate upon this. The phi operate upon br minus. Okay, now dr operate upon r sine theta b phi. Okay. Cool. And then this is what? This is r e theta. R e theta. Ni r theta. You can simplify by multiply r inside here. So the other one is last sekali this one, here to here. Okay, you take this one as the basis vector. So plus also very easy, dr operate upon rb theta minus d theta operate upon br. Okay, and then you have this r sin theta e phi. You can simplify this, but you see, very easy. You just plug in and operate. Okay, you understand? Yeah. Yes, I told you just now. Minus, it will be minus if we operate from here. This one we take the second term, right? So from here left to right, and minus here to right. But positive you take from here to here, and then here to here. Usually you want to take everything positive. So when come to r is theta, you just operate this thing in reverse lah. So d phi instead of this the r this first, this term first. To see. Right on. Very good question. Okay. So you see, your seniors still love to come in and revise, refresh their mathematical physics. Okay, all right. So got it? Very easy. So now we go to the topic for today. Maybe try to finish all this. Maybe cannot lah. Maybe this one. Up to this. This one try next week lah, maybe. And after that we go for tensor mathematics. Quite very interesting. You never learned that before. Engineering people never learn tensor. As engineering people, you just rank 2 tensor only. Stress tensor. We learn up to 4 rank 4 tensor. So this is very important in vector calculus. Consider the three main function or main equation, three main equation in vector calculus, which is being used a lot. Green theorem. So let's see green theorem. All the same. Actually, green theorem is like the fundamental. And then you see the pattern. Green theorem. This is a line, close line, integral, and then surface, and then just a portion of curl, and then this is a surface. Okay. And then go to Stokes theorem. Little bit, always the same, but more generalized. This is also a line integral, close line integral. This is overall curl. This is just a portion of curl. This is overall curl. Okay, this is Stokes theorem. Almost same. And this one is the divergence or the Gauss, being used a lot in electromagnetic field, electromagnetic. This one is AdS. Now, this one is close surface integral. This one close line integral. This close surface integral, and this volume integral. No, close surface is surface volume, line surface. Very easy to remember. If line integral, surface, surface integral, volume. That's it. So very much related. So now we go to the fundamental, which is the green theorem. How we see it? Okay, this one. Okay, I think yes. How people perceive green theorem. The green theorem, I just want to get into the fundamental, and then this one just direct application of this. Well, green theorem is fundamental. How people perceive it. Let's say, for example, even green theorem is being used in general relativity. Even I told you, you can derive the Riemann tensor in general relativity by using green theorem. So let's say, for example, you have this x and then y, and then this is some closed area, right? So from here, the minimum of the x, maximum x from this is x1. Let's say this is what not we call x. This is we say a to b of x, and then minimum of this in what direction? This is we say from C to D. This is the maximum of this line up to here. This is D from C to D. Y. And the thing is x. Let's say x. Let's say y. Okay. D Q D X. Okay. We work with x first. From here, this is the maximum. This is the maximum that y can of y, and this minimum of y, and this area from here to here we see the x2. From here to here, the minimum one is everything is x1. So if you each point, if you want to integrate between here to here, this is x1 here, this x2 here, this x1 here, this x2 here. So this is start from x1. So this is start from for x2. The x2, x1. Like that. Okay, you got it? Got it? Okay. From this maximum point of that touch the y. Okay, from the maximum point to this is from here to here. The boundary here is the x1 boundary. This one is x2 boundary. Okay, all right. So now let's say we differentiate the respect dq dq respect to dy, and then dq respect to dx, and then dx dy. We surface integrate. Let's see what happened if we surface integrate that. So dq dx dy. So this is okay, x from x1, generally x1 to x2. Okay, x1 to x2. Then y is from c to d. So we can just say, okay, by chain rule, dq dx is equal to what? Everybody? dq dx equal to dq, right? dq. Okay, so we can say dc and then integrate x1 x2 dq and then dy here. So you can integrate this dq. So if you integrate dq, you get what? Q. So you get something like this. Okay, C, D, and then Q. Q is a function of x and y. So this is the result already, which is from x1 to x2, and this is dy. Got? dq dx using which is equal to dq, and then q xy x dy. Okay, all right. So this one is become cd q x2 y minus q x1 y. Yeah. Which one? From here. From the integral. X1, X2. Okay, dy. This is dx. Okay, we first dx do. Dx from we take this one because we want to okay, we know because we take this could be anything because this is surface integral. This could be anything, not just between A and B. This between every point on this side, x1, x2, x3, x1, and everything is on this point is x1. You could integrate from here to here. You could integrate from here to here. So that's why, because this one you take x1 to x2. Okay, got it? So, and then y ni yang kita ambil from C to D. Y we take from C to D. Okay, C to D, x1, x2. it's not between A and B, but every point here. Every point here is considered between this point and to this point is considered x1. And then you, let's say, so this thing is like integrate here, here plus here, the whole thing, one whole area of this. You want to integrate area, okay? Now it become dc q x2 y q x1 y. Now it become like close integral. You can get close integral from this equation. So this is d with respect to dy. Okay, so you can separate them, cd, and then q, then x2 y dy minus apa? CD also, CD, and then q x1 y dy. Okay. Then very easy. Take this one. Erase, eh? Right. Okay. CDQ, okay. CD, now you can develop CD, okay, Q, okay, tak apa, I tulis balik. Q, X2, Y, dy, minus CD, Q, X1, Y, dy. Now you can say this thing if you flip CD and then DC. Right? CD and then DC. CD after that DC. If you flip, okay, this CD, QX2 Y dy, and then if you flip instead of D to C, D minus C, you flip C of D, so this one become positive. So this one D, C, Q, X1, Y, dy. If you look at this, C, D, and then D sambung, continue with D, C, C, D, DC, making a loop. This is what we call closed integral, closed line integral. This whole thing is, we can say this one is Q, dy. So Q dy is equal to, tadi dq dx, dx dy. Okay. So this is what CD DC. And if you look at this, if you look from there, the path we integrate is like, first we integrate from x1 to x2. So the path is like this, x1 and to x2. And then C to D, C to D, C to D. So it's the rotation of the whole thing is like the clockwise. Okay. So this is important. Later we have to flip because for P, we want to say there is another thing. Now Q is you differentiate with respect to X. Now later we want to differentiate something with respect to Y. Okay. Okay. This one okay so far? Everybody okay? Now we want to the other one is this. something like this. You want to, this is green theorem, okay? Okay, now you want to differentiate, let's say, something with respect to y. I mean, surface integral of something with respect to y, we say, let's say p, which usually people use in green theorem, with respect to y. And then, of course, dy dx. Dx. I mean, this surface. You see, the thing is now something like this. Okay, oh, I have to redraw again because I didn't put y. Okay, so where is y? So okay, the closed surface, something like this. Okay, something like this. And then there is here. So this is AB. This is CD. Never mind about this because we're not going to put CD anymore. We're going to concentrate now AB. But why? We have to. Now later, just now I put this side is X1. Okay. You want to insert this side is everything from the maximum of Y there. This side is X1 and to the other side is X2. But now Y. Now, the maximum of y, everything from you don't say the maximum of y, no, you maximum of x. The maximum of x is here, and the minimum of x is here, and everything above the minimum of x, above that, this is all the point that we consider as y2. Below this, all the point that we consider y1. From the minimum of the x, maximum of the y of the x for this diagram. Okay, understand everybody? So far okay? So macam tadi tengok, tadi kita ambil the maximum of the y, kan? Maximum of y, every yang sebelah kiri x1, the left one is x1, the right one is x2. So over here, the top one, the minimum of x, the maximum of the minimum of x, the maximum of y, the maximum of y, the minimum of y. Okay, now the maximum of x here, the minimum of y, x here, which is above the maximum of y of x, above the minimum of x, above the minimum is y2. Below the minimum of y, below the minimum of, okay, this one, below this point, the minimum maximum of ni is y1. Okay, so now we can say, okay, start from y1 until y2. Okay, all right. So far, okay. So same thing. This is from dx is from A to B. From A to B. A to B. Okay, we have this, and then the this one become dp, dy, dx. This is y1, y2. Same as just now. A to B, and then this is P x y2 minus P x y1, and then you have dx. Okay. So you can say that you can separate them. A, B, P x y2 minus dx minus A, B, P x y1 dx. Okay. Okay. The best thing is that this thing is this thing, if you look at this, you start from y1, and then goes to y2, kan? y1 goes to y2, y1 goes to y2, y1 goes to y2, and from left to right, from A to B, left to right, A to B, y1 to y2, y1 to y2, and left from A to B. But so it goes this way. Rotation goes this way. So, but we want the rotation always go like counterclockwise, like this one. So the result of this have to be negative. So how are you going to do that? You take, so negative here, you put this, you make this thing become negative. That means B, instead of A, B over A, but we put A over B. A over B, and we have to what we call, put a negative here. So this is P x y2 dx minus A B. Okay, it's already follow the what we call the closed integral. So A B A, and then continue with A B. So it's closed integral, but negative, and then you put here, you take out here the whole thing as a factor. That means this is positive. That means this is negative closed integral P dx. Okay. Okay. Negative closed integral P dx. So now this case is, you put negative here, the closed integral P dx is this one. I mean positive one is one. You put negative, that means it rotate back. It rotate this way. I mean, it rotate this way, A to B, it rotate. I mean, it's just like flip this is the same with this one. So you align with this one when we put negative here. Okay. Yes. Because at first we get this one. The whole, if you inverse the whole, you cannot get the closed integral. For example, okay, let's say now I invert this one. Now I invert this one. Okay, I got this. But then I invert this one. I got AB, but this is BA and then AB. It cannot be closed. Okay, if I invert this one, Oh, okay, this one is because I take out the negative at first. Tadi kan negative kan. Originally, okay, now I invert this one jadi AB, BA, yes? And then let's say I invert this one. This one originally this one negative. It's negative, okay? Okay, because this one I didn't invert, okay? This one I just invert this one. So the thing is now is okay. BA is already closed integral. B to A and then A to B. But if you invert this one, for example, if you invert this one, it becomes this one. So it goes back all around. So you cannot do closed integral here. Okay. Okay, this one C to D, C to D and then C to D. Cannot close integral. So you have to invert this one, C to D. Jadi D become invert, become become tadi mana? Okay, you C to D. C to D and then you invert jadi DC, okay? C D DC now close integral. Okay? Why this one you don't have to make negative, because we want in this direction, okay? X1, X2 and a D, this direction. But this one originally it is a different direction. So you have to reconvert. So you got originally you got this something like that, which is BA kan. BA, this one now it's closed already, but this is negative. Now it closed already, negative. So if you put a bracket here, and then this become positive, this whole thing is PDX. But negative sign. And this PDX, negative PDX is equal to this one. So this one is negative PDX. So this negative PDX is this one. Right? Understood? Okay, everybody? Anybody? Okay. Now the last stroke is to develop the equation of the Green theorem. So PDX, so let's say PDX is equal to negative. Terbalik lah. So buat dy is negative PDX. So PDX negative dP. Don't need to put the what we call the limits already, because we get the pattern. The penting the pattern. So dP dy dx dy. Okay. And the other one is we got last time just now. Okay. Close of q dy is equal to double integral dq dx dy dx or dy dx dy is okay, still okay. Okay, now we got the pattern. So we add them together. So we add them together, close integral p dx plus q dy, you will get the surface dq, the famous Green theorem. This whole, and then this. So this is the Green theorem. The concept of the Green theorem. Green theorem. The Green theorem say that the closed integral of p dx q dx is equal to the surface integral of dq dx minus dp dx dp dy, something like that. Green theorem. And we can use this to calculate all kind of surface area. That's the thing. So for example, you want to calculate the surface area of ellipse, kan? Kalau you can still calculate it by using just calculus, but it's messy, panjang. By using this, very easy. Okay, which one I nak erase? This one, okay. Can I erase this one? Okay, boleh? Can. Okay, now we try to we can see how the power of this Green theorem, the power of Green theorem, it can find the surface area of anything. And the other one is up to, if you learn general relativity, if you take general relativity, if you want to, today I'm going to talk about this. How green theorem can differentiate, derive the Riemann tensor. But of course, I'm not going to talk about this in this class, because you have to learn classic, what you call, tensor calculus first. But let's say, for example, you want to find this. You want to find this area. You want to find this area of this area. Some area of this, you don't know how to find. You want to develop some equation to find this area. Okay? General equation for this area is dx dy. Something lah, some a dx dy, some function of this area. So not a, some function of this area, function x or y. This general equation of this. This is area. Okay, some function. This is a general equation to find area of this. Okay, so A, okay, we can say that is equal to dx dy. Very easy, dx dy. And this dx dy is a function of this, okay, this area. It could be any function of area. So if this, we want to just using mathematical tricks. If you multiply 2 over here, so of course you multiply 2 dx dy. Let's say we don't know the limit yet, and then we want to find this thing. We want to figure out what is this. Okay, so this becomes this. How this happen? You can say that this 1 minus negative 1, so equal to 2 dx dy, and then this is 2a. Okay, now let's say this 1 negative 1, 1 minus negative 1 is you have 2 again. So this 1, so we use this one, this what we call the surface integral that we find, we just dq dx minus dp dy, and then this is dx dy. So now dq dx is what? dq dx is equal to, dq dx is equal to 1. dp dx is equal to negative 1. Okay? dp dy is equal to negative 1. So dy is negative 1. So what is q? Q is dq dx is 1, q is x, right? Okay, very easy. dp dy is equal to negative 1, q is, p is negative 1. P negative y. So this is equal to, this whole thing is equal to, so, and this whole thing is 2a, start 2a, this one is it, and 2a, and then it's 2a, and this is what? P dx plus q dy is equal to this one. Okay, equal dx. So okay, this one dq dx is equal to this thing. Okay, and then still equal to a. And now p we already have p is negative y, and q is x. So we have, you rearrange back, x dy minus y dx. So area is 1 over 2 closed integral, this one. Area is 1 over 2 closed integral x closed integral of x dy minus y dx. So this is a very useful function to calculate area under any shape. For example, shape that is, we're going to talk about this, shape of ellipse. Okay. To the equation here. Wait, I want to check. X dy minus y dx. Dy minus y dx. They're very now. Okay. Let's say we want to find what? We want to find ellipse. B A ellipse. I mean, this is my drawing is not so good, so this should be the same lah. B A. So this one is B. This one is A. Okay, elliptical. So do anybody know about the area of the formula for ellipse under this area? AB. Anybody know? Pi, actually pi multiplied with AB, the area. But of course, people may calculate by using calculus or by using, you can use this. You can use this, okay? So from here, you get this x and b. So x, so you can say that x is a cos, let's say phi. So this one is phi, okay? Or rotation from here, 0 to here to here is phi. Let's say it's xy. Okay, xy. So x a cos phi. So if cos is, if phi is 0 here, so x is to a, right? If phi is 90 degrees, okay, x okay. Now y is b sine phi. Okay, so if phi is 90 degrees, phi is 90 degrees. You see, phi 90 degrees is this one. When phi 90 degrees, so phi 90 degrees is this one is 1. So y is equal to b. Phi 90 degrees, y is equal to b. Is phi 90 degrees. Okay. And then if phi 0 degrees, then x is equal to a, x is equal to a, right? Okay, understand? So you can look at this, you can exactly write this thing. Okay. A cos phi or b sine phi. Right, that's the thing. So we want to plug into this equation. We want to find a. So x dy, y dx. So now we have x. What is dx? So they have a dx term here. So dx is you use, so x is a function as a function of phi. Right? X is a function of phi. This chain rule. So dx is to dx d phi d phi. Okay. So you can say that this is dx d phi is negative a sine phi d phi. So dx is negative a sine phi d phi. So kita tengok pula y is to b sine phi. So dy is dy d phi d phi, which is b cos phi d phi. This is dy. Just now we just plug into this. Plug into this x dy. X dy, where is x? X is here. A cos phi. And then multiply with dy is b sine phi. Okay. This one b cos phi. B cos phi d phi. Okay. Okay. B cos phi d phi. D phi we take out. So a cos phi, b cos phi, d phi is 1. So x dy minus y. Y is what we have, b sine phi multiply with dx, kan? Multiply with dx, which is where is dx? Dx is this negative. See, it comes beautifully d phi. Okay. So what we have here is half close integral ab cos square phi d phi plus ba same thing, sine square phi d phi. Okay, we can take this out as half ab cos phi plus sine phi d phi. So this one is 1. Okay. So what we have here is are you ready? This one? Okay. So what we have there is a is equal to half. This one is ab cos square phi plus sine square phi is 1. Okay. Trigo identity d phi. Take out, this is constant, take out ab over 2 close integral d phi. Now what is close integral of d phi? Very easy. This is if you look at this one, the ellipse, 0 goes up until 2 pi. From 0 goes to, from 0 here, coming back 2 pi, one whole circle. So you can say AB over 2, 0, no more, just, that means close integral of d phi here is equal to 0 to 2 pi d phi. Okay, 0 to 2 pi d phi. So we have AB 2 and then phi from 2 pi to 0. So we can say AB 2 pi over 2, which is A pi AB, which is the area of an ellipse. Okay? You can work this with any shape. Circle, you can prove the circle equation. You can prove the even square. You can prove. So apa lagi example? I have another example of this. Okay, now we go to Stokes lah. Stokes theorem. Stokes theorem, okay? So we have done this. Now we go to Stokes. Now we go to Stokes theorem. So far okay? Green theorem okay? Very easy, yeah? So green theorem, you play around with that. dot D. So which line we want to calculate? The borderline of this line, the borderline of this geometry is this one. The x, y, z is at the xy plane. And so we want to create the border here. This is the line that we want to do. We want to do the close integral. So we're not going to do here because we don't know the line. But this one, the border of the line here. So we can say that this one is x squared plus y squared is equal to z squared is 1, but z is to 0. Z is 0, which is equal to x squared plus y squared is 1. So the radius is also 1. So this is the border line, the border or the line that we want to integrate. So when z is to 0. Okay? So we can reduce this thing. You can reduce this thing. You can reduce the expression. A dr is equal to z is 0. You can cancel all these things. What left is this close integral of 2x minus y dx. Very easy. Okay. You don't need to know the line of something here. Just get the line that is close integral is the line on the xy plane with the border between the surface, the half sphere with the xy plane. So z, where the line is at z 0. So the vector field yang ada sini, where they have z function is all, you can put it 0. What left is really easy. So now tinggal this. How you want to do this? You can either, it's very difficult to use Cartesian coordinate. You have to use this one, spherical coordinate. This one is P. The angle that rotates here, representing the one closed circle, is P. The angle P. We look from top, your eyes here, top to the angle something like this. So this is one whole circle. So this is x, y, x, y. So start from here, goes to here, so 2 pi. One whole circle, 2 pi. So it is 0 to 2 pi. That means you want to convert all these things to spherical coordinate. No need to go to spherical, just on this plane, xy plane. No need the whole circle. So if you want to put a spherical coordinate, x will become r sine theta cos phi, right? Yeah, something like that. Okay. Just on a circle. So this C, you can use a cylindrical coordinate. So dV, don't need, it's not just this. So just the surface on the plane. So dx, okay. Now we cannot say simply dx, okay? We have to convert this thing, okay? Okay, so this is the equation is A
Might put to 0.
dot dr. Now it is reduced to 2x minus y and dx. Now, if you imagine you have your eyes here, you look downward, so you have something, so you have x forward, y, so how you can rotate, so it's easy for you. You have x, y, so this is 2, 5 from 0, rotate is 2 feet. So x here, that is r. So x over r, so we can say x, we can, no need to use spherical or x over r is cos phi. So this whole thing is phi. X over r is cos phi. Y over r, y over r is sine. Okay, rotation. Okay, now we have, so r is, we know already r is 1. So this x is the cos phi, y is the sine phi. So but we have here the x and y we just plug into there, but now the x, so we use the change rule, the x phi. So the x is phi, which is negative sine phi, and then the phi. So the x is negative sine phi phi, so you plug into here. Now a dr is equal to 2x over 2 times cos phi minus what? Minus y. Y is sine phi, and then multiply with what? Negative sine phi dv. Okay. Which is, look at this, 2 cos phi sine phi, okay, negative plus sine square phi dv. Negative. So from the phi is from where? From 0 to 2 pi. Okay. So how we want to integrate this?
Oh,
Okay.
ada.
Yeah, you can use 3-4 item. Very easy. So in this course, it's like all you have been work with technique 1 plus technique 1, technique 2, whatever kan, combine together. Everything got in there. So you go ICT. Which one I want to? This one okay? Okay, everybody. Okay, no, semua okay? Ini laju sangat ke pun slow? Laju. Okay, I slow down. Lagi slow. Tapi, you know how
Kau pandai
we
boleh
got
kan?
here, tahu kan?
Kau pandai cara main dia.
Okay, so far okay? Then dapat dia. Very easy kan? So now kita integrate that. This one is just 3 quantity lah. 0 to pi negative. We put the possible sine square sine square phi minus 2 cos phi sine phi, and this one you cos phi. More familiar, you just balikkan. This look more familiar to you. And then this is d phi. So we just want to convert this to something that manageable to integrate. We integrate this one is very difficult, but you know for this one, if you look at this sine square phi, you just remember there is one cos 2 phi, okay? Cos I just refresh you all that cos A plus B is angle cos A cos B minus sin A sin B. Okay. So kalau cos two phi. Cos 2 phi is cos berarti A, namanya A is phi, this one also phi. So 2 phi, so this means cos square phi minus sin square phi. So just remember this one, maybe you all remember what this one from form 4, form 5 dulu. Okay, now cos 1 minus sin square phi, because we want to convert to this sign. What is this sign? 1 minus, so there is also identity cos phi plus sin phi is 1. Okay, so cos square phi 1 minus sin minus sin square phi, so 1 minus 2 sin square phi equal to cos 2 phi. So we can say that sin phi is equal to 1 minus cos 2 phi. One is divided by, so this is manageable to integrate. Okay? Because sin square phi is 1 minus cos 2. You integrate cos 2 phi, you dapat negative sin, you dapat sin 2 phi over 2. Okay? You differentiate sin 2 phi over 2, you dapat cos 2 phi value. Okay? Very easy, manageable to integrate. So this one can be plugged into here. Okay? Now kita tengok this one. It is that one. Okay, everybody.
Okay.
Kau boleh? Memang kaplah sini.
So cos what go? Well, the one is what? 2 sin theta sin p cos p. You remember dulu sin A plus B. This is sin A cos B plus sin
B cos A.
Okay. So if sin 2 phi, that means phi here, so that means sin phi cos phi plus sin phi cos phi, that means very easy. So directly, okay, go to, so now we can solve the equation. 2 pi, jadi 1 minus 1 minus 2, 1 over 2 minus cos 2 phi over 2 plus sin 2 phi. Okay. So 2 sin phi cos phi is 2 sin 2 phi. So d phi. So this one very easy. You can solve already. Manageable to solve. Phi over 2 minus, okay, sin 2 phi over 4. Okay. Kita dapat cos 2 phi 2. This one minus cos 2 phi over, then you break pi 0. So you have 2 pi, put into here, 2 pi over 2 is pi minus sin 4 pi, 4 pi over 2 pi 4 pi over 4 minus cos 4 pi over 2 minus and then 0 0 0 0 to here jadi plus this one sin 0 over 4 and then plus cos 0 1 okay 1 over 2 cos 1 cos 0 jadi 1 di cos 4 pi also 1 4 pi I mean 2 pi another one is 4 pi which is 0 jadi 1 jadi 1 over 2 negative 1 over 2 plus 1 over 2 0 answer is 0 is 0 0 so what left is one is 0 sin 0 sin 4 pi 2 pi 4 pi 0 what left is pi okay pi what left is pi point pi so the whole thing is a dot r is 4. So let's check whether the other side is also pi. Okay? And then you try to compare which one is easier to solve.
Mana itu man? Dah keluar. Hah? Bagi tahu. Apa dah?
Okay, everybody. Okay.
Doktor, dah 12.59 dah.
Huh?
Dah 12.59.
Okay. Okay, you can try yourself. Okay, try yourself by doing thinking and try to solve this.
Ini salah aku. Habis doktor lihat tak semangat ke?
Got ni kita susah sikit kan. And df ni jadi df dx dy yang tadi I explain tadi and then k dot n. You will get this thing easy, you get k. And then jadi dx dy saja. And then this is for integrating it. So it is pi over r squared, this is pi. It's very easy. But you try yourself. Okay, everybody? Okay.